Hi guys, welcome to my review. Today I am going to be talking about quantum numbers and their orbitals. So I'm super excited. I know there's a bit of a glare right there. I'm so sorry. I spent like 5 minutes trying to figure it out, but guess we're just gonna have to deal with it. But today we're gonna be talking about quantum numbers and orbitals. And I remember the first time we talked about this lecture, my brain literally hurt so much just trying to understand what was going on, what poor Dr. Morrison was trying to explain. But I have a pretty good analogy that I'm excited to explain to you guys that will help kind of visualize what's going on, what the concept of orbitals are, what the different quantum numbers are, and just the entire idea of what it is. And I know it can be really confusing, but I'm just going to try and do my best to explain it for you guys today. So let's get started. So in order to start off, we are going to be talking about what orbitals are. And now, a lot of you guys have had a common misconception of what atoms look like, the classic atomic model that is used throughout everyday society. So a lot of you guys imagine orbitals as you've got your electron right here, or your nucleus right here. You've got your different circles, they're going around, and then you've got your electrons spinning around. That's just kind of a rough idea of what you guys think at least what I thought the atoms were for a long time, but this is incorrect. There's a lot of things wrong with it, but for starters, the idea that there's just orbits that are in one way and that the atom just goes like round and around like that, or the idea that the atoms follow a direct path, all those different concepts are very incorrect. So instead, what we have to think about with electrons is the idea that, so basically when you are taking pretty much any average, if you've ever taken statistics, you've got your little bell curve, right? Your dots randomly, and at some points there's going to be a really high percentage of dots, and then for certain areas there's like a pretty low percentage, but then there's like still a possibility, then there's other sections where there's just no possibility. So we kind of need to start thinking about orbitals as that, is the idea that there's this area where orbitals can exist, but certain areas the orbital is more likely to exist, and certain areas the orbital is less likely to exist, and there are certain areas where the orbital can't exist at all. And so let me draw it more kind of accurate. So let's see right here, we've got our nucleus. Let's say electron is really likely to be close to the center. So at different points in time, it's really close to the center. And certain times it's here, but then somewhere about here, the electron isn't going to go outside of the nucleus past the circle. And so we've kind of taken this imaginary visualization in order to create an orbital. So that's kind of what orbitals are. It's basically just the possibility of where is the electron. And it's really difficult to figure out exactly where the electron is at a certain point and what the orbital looks like and all these different things. And another thing that is interesting is for each atom and each electron and each orbital, there's a different orientation, a different way of how it looks. So that's what quantum numbers come into handy is. We want to be able to look at an electron and decide what orbital is in, what does the orbital look like, and how is that electron moving, what does that kind of look like. So now that you kind of have a concept of what orbitals are, we are going to move on to quantum numbers. And I know the first time I heard quantum, I was like quantum physics, and I thought it was really hard, and it kind of is, but if you take a step back and look at it visually, then you'll be able to understand it a lot more. So for the first part, there are 3 different quantum numbers that can be used to describe the orbital. So there's 3 different quantum numbers, and these 3 quantum numbers they describe the 3 different characteristics of an orbital. So we're going to start with the first quantum number, see how it goes, and then we'll just keep going along. So the first quantum number is n, which is the principal quantum number. Principal, I hope right now in my recording it's reversed, but hopefully when you're watching this, it's not. If it is, I apologize. But the first quantum number is n, and it's the first quantum number that will be, when you're listing the quantum numbers, this is the first one that'll show up. And what this quantum number is it is describing the energy level and the size of the orbital. So, for example, well, let's not start with examples first. First, let's start with explaining what the different energy levels are. Obviously, each orbital has a different energy level, and you can't have an energy level of 0, otherwise the orbital wouldn't exist. So every orbital will always have at least n equals 1. And here we've got a little line of energy levels. So let's say n equals 1 goes up to here for the energy. So here we've got our energy, n equals 1. Well, we could also have n equals 2. And n equals 2 is a higher energy level than n equals 1. And we could have n equals 3 or n equals 4. But as you continually go up in energy levels, if you notice, the distance between the energy levels decreases. So I didn't draw this great, but the energy level jump from n1 to n2 is really big. From here to here is pretty big. Wow, those are terrible lines. Those are very bent. I'm sorry. The jump from n equals 1 to n equals 2 is pretty big. But then as you go from n equals 2 to n equals 3, it shrinks and shrinks and shrinks and shrinks until eventually when you're jumping from n equals to 70 to n equals 71, the energy jump is like this big compared to when it was this big. So as you're increasing energy levels, the amount that it increases decreases. No, that was kind of confusing, but these are the different types of energy levels. So each number associates to the different energy levels. So n equals 1 is the lowest energy, 2, 3, 4, increasing in energy level. It also describes the size. So the n equals 1 orbital, let's say it looks something like this. It's just a cute little dot. And we've got n equals 2, which increases in size. So we've got n equals 3. And then finally, we've got n equals 4, which is just way bigger. And the reason for this is there's more energy because these orbitals are holding more electrons. And as they're holding more electrons, obviously the atom size is going to get bigger. So we've got our different energy levels. And as always, we will be busting out the periodic table to explain this, but the periodic table is amazing because it has already been organized for you. So if you look up here, we've got hydrogen and helium on the first row. And this is the n equals 1 energy level. And then as you move down a row, it's n equals 2. Then this level is n equals 3. And if you're guessing which one this is, I'll give you a second to think about it. This would be n equals 4. So as you go down the periodic table, each row has an increasing energy level. So that's a really good way to keep track of what energy level you're on. If you're trying to figure out the energy level for an orbital that is in bromine, then you would just start from here, 1, 2, 3, 4. So it's likely going to be an n equals 4 energy level. So now that we have talked about energy levels, I'm going to hurry and pause so I can erase and rewrite the next quantum number. Okay, so now we are going to move on to the second quantum number. So on the corner, you can see right here, we've got n equals energy level. So that is the first quantum number. And the second quantum number we're talking about is L. And L describes the angular momentum quantum number. Well, sorry, L is the second quantum number, and it describes the angular momentum. Now, if you're like me, you're like, what the heck is angular momentum? Good question. So the angular momentum is basically the shape of the orbital. So there's a lot of different shapes, and as you increase, or sorry, not as you increase, but as you move from angular momentum to the next one, the shapes get more and more complex. So we're going to start with the basics, describe those, and as we keep going on and on, you'll see that the shape of the orbitals gets more complex. So the first shape we've got is, I remember for N, we talked about how no energy level can be 0. If it has electrons, then it has energy. So it has to be at least n equals 1, but this is not the case for L. For L, we can start right at square 0. So all the different possible L numbers are 0, 1, 2, 3, 4, and it can just go on and on and on. But the main thing we will talk about is the first 4. Sometimes you'll need to know L equals 4, the fifth size, but not really. These 4 and even L equals 3, we don't talk a lot about, but I will cover at least some of them. So for the first one, we've got L equals 0. And this shape, going back to what we were using to describe the energy levels, is just a nice circle. It's the most basic, simple orbital shape, so it's really easy to remember, but this is L equals 0, and it's nice because one trick you can remember is 0, it looks like a 0. So that is the first energy, or that is the first angular momentum shape. The second angular momentum shape we've got is kind of a little figure 8. And we're talking about a little nice X and Y axis. So if you see, first one's got a nice little circle shape, but then the second one has 2 little loop-de-loops. And that is L equals 1. The next energy level we've got is getting a little bit more complex, like I was saying. They're always so hard to draw. It almost looks like 2 little figure 8s, but it's more of like a 4-leaf clover-ish. So we've got L equals 0 right here, L equals 1 right here, and then L equals 2 right here. And then L equals 3 and L equals 4 get more and more complex, as I'm sure you guys can assume. It would start to add a lot more complexity to it, so there would just be a lot more dumbbells. Sometimes you've got shapes that look like this, where there's intercepting with each other, and it just gets really, really confusing. So the main thing you need to know is shapes-wise, be able to identify L equals 0, 1, and 2. Now, I'm sure you guys are thinking, when you're describing an orbital, you're going to list each number in a row. So let's say you've got an energy level of 2, and then your shape is going to be 1. Well, you would write 2, 1, but then do you put a comma in between it? Do you do a dash? How do you make it clear that it's 2, 1 and not energy level 21? Well, what scientists have done is instead of using numbers for the L value, instead they've assigned different letters to the shapes. So what they've done is they've assigned it so it's S, P, D, F for L equals 3, G for L equals 4, and then the numbers go on. The big 3 though, or the big 4 I guess, is the S, P, D, F. And these are, each letter is associated to the shape of the orbital. And I have come up with a little acronym for you. So if you're watching this video, you're welcome. But the different acronym is it's super powers don't fail. So one more time, super powers don't fail. And as long as you remember that superpowers don't fail, you can remember the order of the angular momentum. So you've got 0, you've got S, 1, you've got P, 2, D, 3, F. Superpowers don't fail. And if you look at the shape, each shape is associated with a different letter. So let's go back to our practice problem. We said it was going to be 2 and then a 1. But if we look at our L equals 1, what letter is that? That is the P angular momentum. So this would be an SP orbital. So now that we've got an SP orbital, what would that look like? Well, it is this energy size 2, and it is a P orbital. So we wouldn't be drawing a circle, we would be drawing a little figure 8. I'm going to give you guys 3 different options, and you think in your head which one you think it is. Oh wait, hang on, that was a terrible, terrible orbital. So we've got 3 different orbitals. Which one do you think is 2P? Is it the really small one, middle, or big? And I'm going to tell you guys, it is the middle one. So this one would be in 1P. It's got an energy level of 1, which explains why it's the smallest. And then this one has an energy of 3P, which would mean that it's bigger than this one. So the middle one would be 2P. And this is not up to size. And I don't even know if the ratio is correct, but you should be able to, and I'm sure in Dr. Martinson's test, he would label this one as a 3P and this one as a 1P. And if it's in between the two, then you could use deductive reasoning to assume that it is a 2P orbital. So we've got our N, which is the energy level, and then our L, which is the angular momentum. And for the angular momentum, the L tells us what the shape is. So for N, we know what size it is. For L, we know what the shape of the orbital is. So now let's look at the periodic table. Like I said, this is your map. This tells you what everything is and where it's going. So as we're going down the row, that's going to tell us the energy level. But then each section is actually helping us tell what the orbital shape is. So over here in the S, we've got, or over in this row right here, we've got the S orbitals. So all the round orbitals right here are going to be in this little section right here. Then we're going to jump over the transition metals and go to this big old block right here. And this is where all the noble gases are, a lot of the metalloids, non-metals, all of this. Right here is the P. And so all the orbitals over in this area are going to be nice and figure 8 shaped. And then the transition metals are going to be D, which is right here. And then down here at the bottom, this row is going to be F. Sorry, F. Those are the F orbitals. So you feel free to memorize this, practice this on your periodic table of elements. This is your map. So this is going to tell you the energy level N, and then depending on where it is the shape. And then finally, remember, superpowers don't fail. Okay, we're going to move on to the third quantum number, but first I'm going to erase and reset. Okay, now we're ready to move on to the next quantum number. So we've got our list going. N is the energy level, which is the size and the energy level. Sorry, N is the principal quantum number. That's the name of it, but it's the energy level and the size. L is the angular momentum quantum number, and this is telling you the shape of the orbital, so whether it's a figure 8, it's a circle, it's the 4-leaf clover, all the different shapes. And then M of L is the magnetic quantum number. And what this one is this is telling you the orientation of the orbital. So for example, we've got our orbital over here, this guy, nice and cute, but who's to say it's not going to look like this to the side? Or maybe it is side to side on the x-axis. So what this quantum number is going to do is it's going to tell you the orientation. So it's still the same size, it's still the same shape, it's just twisted and angled differently. And for the magnetic quantum number, there is a little equation that you can use to figure out all the different options. So for energy level, we know it always has to be greater than 0. You can't have an energy level of 0. And so it's 1, 2, 3, 4, all the way on and on and on. For L, we know that it can start at 0. It can be 0, 1, 2, 3, all the way up and up. And each number for L is associated with letters, which is superpowers don't fail. But for the magnetic quantum number, we're going to use this equation, which is M of L is always equal to 2L plus 1. So, for example, let's say we've got a number that is N equals 2 and L equals 2. Now let's think. 2, what would the letter for this be? Well, 0 is S, 1 is P, and D is 2. So then technically this would be a 2D. Or right now we're not worrying about letters, we're going to worry about the numbers. So L is equal to 2, which would mean that the magnetic quantum number is going to be 2 times 2. So we fill in the L right there because we're using a L equals 2. 2 times 2 plus 1. So we've got 4 plus 1, which equals 5. So there are 5 different possible magnetic quantum numbers. Now these magnetic quantum numbers can be both negative and positive. So what we're going to do is we're going to start out, if it's 2, we're going to start out with ML. There's 5. So this equation tells us how many possible magnetic quantum numbers there are. So there's a possibility it could be negative 2. It could be negative 1. It could be 0. It could be 1. Or it could be 2. So it's the range of L, which is equal to, but it's all the different numbers in between. So an example of an orbital could be N equals 2, L equals 2, and then M of L could be negative 1. Or it could be 0, or it could be 2. Now the question is, could M of L equals 3 in this example? And the answer is no, it cannot, because it is exceeding the L number. And this is the range that we have to stick within for this orbital. And so this different, what the number is telling you, negative 1, negative 2, is just telling you the different orientations of the orbital. So I'm going to hurry and pause so that we can talk about our last quantum number because I'm running out of time. Okay, so the final quantum number we're going to talk about is M of S. Now, up to this point, these 3 quantum numbers all describe the orbital. So remember, these are the orbitals, either this guy, or this guy, or this guy. These are the different orbitals, but the last quantum number talks about the electrons in each orbital. And if we go back to the review that we talked about Dr. Morton, we'll remember that every orbital has has a maximum of 2 electrons. And we've got two different electrons, and then according to the Pauli exclusion theory, there has to be a maximum of 2 electrons in each orbital, and these 2 electrons have to be spinning opposite ways. They can't be spinning the same way. So for the magnetic spin number, there's only 2 possibilities. The electron can either be spinning positive or it can be spinning negative. And we indicate that with either a plus 1/2 or a negative 1/2. And depending on what each one is, it'll either tell you if the electron is spinning positively or negatively. And what exactly that is, I'm not sure what the orientation is. That's a lot of science that I didn't cover. But all you need to know is that this will tell you each orientation. So it is possible to have a positive 1/2. It's possible to have a negative 1/2, but you can't have 2 electrons that are both negative 1/2. They all have to be spinning opposite directions. So when you take all 4 of these quantum numbers together, this will narrow it down to exactly 1 electron. And no 2 electrons can have the exact same number of quantum numbers, because even if they're in the same shape orbital, even if the orbital is the same size, same shape, same orientation, the 2 electrons in each orbital are going opposite directions. So the final spin quantum number differentiates the electrons. So the first 3 describes the orbital, and the last one describes the electron. So now you're probably wondering why I have car stuff. Sure, that's what you've been wondering this entire time, hanging on the edge of your seat. Well, I have come up with the most amazing analogy in the world. So if you're ever confused, you have to think about the different quantum numbers as describing a racetrack. So here we've got our different racetracks. I have tape that I'm going to use to tape up my different racetracks. And each quantum number describes the racetrack. So we're going to start off with N. So N is the energy level. And this energy level is going to tell you the size of the racetrack and the energy and how much money it costs. So if you've got a really baby racetrack, then it's probably going to be an N = 1, maybe N = 2. Now, if you've got like a massive Texas Motor Speedway racetrack, it's going to be like an N = 10, 11, 12. It's going to be a huge N = number. So the N tells us how big the racetrack is. L is the angular momentum, and this is going to tell you the shape of the racetrack. So here we've got just like a really simple 1 loop and done racetrack. But here we've got a little figure 8 racetrack, which is very similar to the P orbital. Remember, super, it's like a circle, P, like this. And then I couldn't find an orbital that looked weird. And I don't know if you can see this very clearly, but if you look closely, it's just like a hot mess. So as the L number increases, then it's going to be more and more intense and more elaborate, but it's all one racetrack. So I know some people will look at the either the F or the G orbitals and be really confused because they see like 7 or 8 different lobes. But just remember, it's still one racetrack. It just is a lot more elaborate and a lot more confusing. Then we've got N = L, which is the ML, which is a quantum number. And I don't know if this is exactly correct, but kind of how I thought of it is the orientation. So you've got your racetrack like this, but what if the racetrack is facing north instead of south? Or what if it's facing east? Or what if it's sideways? So then the M(L) quantum number describes the orientation of the racetrack. And then finally, we've got the spin quantum number. And in each racetrack, you're only going to have 2 cars on the racetrack. And these cars, normally cars want to race against each other, right? But in chemistry, these cars don't want to deal with each other at all. They don't want to compare each other. They want to be completely opposite of each other. So they're going to be driving in opposite ways. So almost think of it as like you've got cars on the right going this way and cars on the left going this way. They're always going to be going in opposite directions. So what the M(S) tells you which racetrack driver you've got. Are you going this way around the track? Or are you going the opposite way around the track? So let's review one more time, and then I'm all done with my review because I'm running out of time. But N = energy level. This is going to tell you how big the racetrack is, how big the orbital is, and the size, the energy level of it. The angular momentum number is going to tell you the shape of the racetrack or the shape of the orbital. And we've got the 4 main types of orbitals. Superpower, don't fail. Superpowers don't fail. And so for the N energy level, as we go down, we increase in energy level. For the angular momentum, we've got the different sections. Super, powers, don't fail. And for the magnetic quantum number, this is telling you the orientation of the racetrack. Is it facing south? Is it facing north? Is it tilted to the side? All the different types. And then we've got the quantum spin number, which is telling you which direction the racetrack driver is going in. So I'm going to give you one example, and I'm just going to write the example, give you guys a few seconds to try and guess. And first off, you're going to tell me if this is a legit quantum series, and then what it would look like. So we've got okay, so if you can't really read, it's 2s 0 negative 1/2. So we're going to go to each quantum number. The energy level is 2, so it's going to be about like this size. Then the s, what shape is the s? Well, let's think. S is the first one. Superpowers don't fail. First one, and the first shape is just a nice figure O. So this is the shape of our orbital. And I just wrote a 0 because if you remember, the s is also the same as L equals 0. Because remember, the L can be a numerical value or it can be a number value. It's the same thing. They just replace the numbers with letters to make it less confusing. L equals 0, which means that the M of L number can only be 0. Now, if this was a 1, then it could be a -1, 0, or 1. But because it's a 0, then there's only one orientation, which makes sense because a ball is a 3D circle. There's only, like, it looks the same no matter where it is. So the L is 0, and then a -1/2. So we've got 2 electrons. One's going positive, one's going negative. It would be describing the electron that's going negative. So by using these 4 quantum numbers, we are able to narrow down exactly what electron they're being described. Now, if you have any questions, feel free to reach out to Dr. Morrison, but I really hope this review was helpful. It was really enjoyable for me. I really liked my race car analogy. So feel free to take a picture of it. There's the little diagram, and good luck on your test.